This time it is.
Okay, welcome everyone. We just heard an excellent talk by Melinda Soares-Furtado. She will speak in a few minutes telling us about complementary aspects of what we heard, and we learned a lot so far. We'll learn more in a few minutes. We will start today with Warren Brown, our own, who will discuss white dwarf binaries as a gravitational wave source. And for Lisa, that would be a very important source that we have to observe before we go to the rest of the universe and identify sources out there. And then we'll hear from Matt Orr from Flatiron, New York City, over there. He will tell us about spiral arms as metal freeways, Azimuthal metallicity variations in simulated spirals. Then we'll hear from Ulrich Steinwandel. He's also from Flatiron, so I guess you came in a binary. And he will tell us about the origin of multiphase galactic winds. And finally, we'll hear from Melinda about unveiling young, nearby exosatellites with infrared space-based surveys. Warren.
Thank you, Avi. Oh, is this too loud? So, given all the recent discussion of visioning and facilities, I thought I'd start by digressing for a moment and just say a word about how do we do science. So one extreme is we all work together, all the resources and people, on a single project. The opposite extreme, I say, is we all work on different projects, 100 people working on 100 different ideas. Most things in science are power law distributions, right? To have 10 good ideas, you kind of need 90 less good ones. And there's no way to know in advance which is going to really be the high impact result. And so I think for facilities, arguably the most important are our general purpose observatories, telescopes that are equipped and supported to address a broad range of ideas, able to execute projects for a broad community of observers, and capable of doing things that we haven't even thought of yet. Of course, there's a place for dedicated missions. This plot illustrates the gravitational wave spectrum from kilohertz to nanohertz frequencies. And there's no way to detect gravitational waves without a facility like LIGO. If your goal is to do multi-messenger astronomy, combine light and gravitational waves, then what you really want is the LISA observatory that will detect millihertz gravitational wave sources. Because everything from the host galaxies of merging massive black holes to compact binaries in our own Milky Way, they emit light. And so let's go back to my talk title, which is about the intersection of light and gravitational waves in the context of white dwarfs. So measurements. In optical, stars are black bodies, which means that our optical view of the universe is basically the Stefan-Boltzmann law. You know, the optical luminosity of the star is proportional to its radius squared times 10 to the fourth power. And this is why a white dwarf and a red giant star, despite having radii that differ by a factor of 10,000, can have comparable luminosities, because white dwarfs can be much hotter, 100 times hotter. And this also explains why, of all the various stages of stellar evolution and weird classes of variable stars, most of what you read about are things that are hot and or giant stars, because that's what you can see. The optical view of the universe is also seen through the lens of the inverse square law. Light spreads out in all directions, and so the observed intensity of light drops off as the distance squared. That means that rare but luminous classes of objects can have comparable apparent magnitudes to very common but dim, intrinsically dim classes of objects. And yet to observe a rare class of object, you have to go to a large enough depth to find one. And you're very often overwhelmed by many large numbers of uninteresting things. And so as an observer, you have to design a project. And I was undertaking a survey targeting faint B-type stars, stars that should not exist deep in the halo of the Milky Way unless they're ejected there. When we found some white dwarfs that should not have been there either. So white dwarfs, as you know, are the remnant cores of stars, the final stage of stellar evolution for practically every star in the universe. The white dwarfs today have a typical mass of about 0.6 solar masses, and that reflects the time it takes for a single star to evolve into a white dwarf. My colleague Michael McKilloch realized that the unexpected white dwarfs we were finding were 0.2 solar mass objects. Now, the universe isn't old enough to evolve to create a low mass white dwarf like that through single star evolution. Binary evolution is required. And indeed, time series spectroscopy revealed that all the objects we observed in our extremely low mass white dwarf survey, the things we would call ELM white dwarfs, were indeed binaries. And not just any binaries, but these were binaries, double white dwarf binaries, with orbital periods less than a day. 1 in 6 systems had orbital periods less than 1 hour. That means that these are millihertz gravitational wave sources. These are among the first objects that LISA will detect when it turns on. So what more do we learn from gravitational waves that we don't already know from light-based measurements? Well, I've referred to a white dwarf's mass, and mass is indeed a fundamental property of practically everything in the universe. But the truth is, mass is not observable. So with light, you can measure directly distance from parallax. Photometry gives you temperature and luminosity. And for binaries, you can, with time series photometry, you can look at, measure the orbital period change, inclination of the binary, radius ratio from eclipses, but not mass. Spectroscopy gives you temperature and surface gravity, surface composition. For binaries, rate velocities give you the rate velocity amplitude, period, and also constraint on the mass ratio for single-line spectroscopic binaries. The reality is that there's essentially no, or very few, eclipsing or double-line spectroscopic white dwarf binaries known. That means we don't actually have a direct constraint on mass for the vast majority of the systems you care about. And this actually matters for the outcomes of these binaries. So white dwarf binaries, so orbital periods less than about 20 minutes, are rapidly losing orbital energy to gravitational wave radiation. They'll merge on million-year timescales. And the outcomes of those mergers depends primarily on the mass ratio of the two white dwarfs, but also on secondary parameters, such as spin-orbit coupling due to tides. So white dwarf in compact binaries, surprisingly, are actually not cooling down with time like every other white dwarf in the universe. They're actually heating up due to tidal heating. And no one knows how efficient this process is. But it matters to the final outcome of the mass transfer stability, whether two white dwarfs explode or merge into a single more massive object. Now, one way to constrain tidal heating is to look for an extra amount of period change, extra amount of energy loss in the orbit, over the amount due to gravitational wave radiation. The problem is you actually have to know the masses well enough to see if there's an extra amount over what the GR value should be. Well, enter gravitational waves. So gravitational waves are typically quantified by strain, which is related to a combination of the orbital frequency of the binary's chirp mass is a combination of component masses, distance, and in the twiddle there is inclination and polarization terms. And it turns out there's too many unknowns in that equation for you to solve them uniquely with just the gravitational wave measurement alone, at least for the compact binaries. Most of those look like constant frequency sources to LISA. And you can try to tease this apart if you have additional parameters like a period change, and you assume that the period change is due only to gravitational wave radiation. But that's actually not true for tidally distorted detached white dwarfs, or certainly not true for mass transferring binaries like AMCVNs. And those are the interesting systems. Well, luckily, white dwarfs emit light. And we already know about some of these parameters. LISA can only localize the best binaries in the galaxy to maybe a square degree. But thanks to Gaia, we know the positions of these objects to a micro arcsecond. Right? That's a delta function to the gravitational wave measurement. And there's no need to solve for that parameter. And similarly, light-based measurements provide a strong prior on distance and period, and in some cases, period change and inclination. And it really matters. So for our example of our 12-minute period binary, J0651, people have shown the combination of the light measurements plus the gravitational wave measurements you expect would improve the gravitational wave parameter uncertainties by a factor of 40. And so these double white dwarf systems turn out to be really great laboratories, for doing multi-messenger astronomy, combining light and gravitational waves. Well, LISA is, there we go, not expected for the mid-2030s. So there's some things we can do between now and then. This figure from Lamberts et al. Shows what LISA would detect for a model galactic binary population of double white dwarfs plotted in equatorial coordinates. The galactic center is over here. And the ellipses are LISA's 1 sigma positional constraints on the simulated binaries. So you can see the spatial distribution is heavily concentrated in the galactic plane, because that's simply where most of the stars are. But the predicted frequency and strain distribution is actually much more model dependent. Depends on how you evolve binaries through 2 stages of common envelope evolution to end up at these sub-hour orbital periods you actually care about for LISA. But there's a paper to be written here, because we actually have a complete, well-defined sample now of over 100 low-mass white dwarf binaries in the northern sky. These objects are targeted by color, temperature, and apparent magnitude. And so we can fairly sample independent parameters like orbital period. And people have started to do this. This on the left is a plot by Lee et al. Comparing mass ratio distributions from simulations to observations. But it's not just mass ratio. We can look at period distribution as well. On the right, you can see period versus mass of the white dwarf you see. And the fact that there's structure in these plots tells you that there's different evolutionary channels forming these objects. And we have enough objects to actually break apart these objects into sort of disk and halo populations and do some tests. So there's definitely some next work to be done here, comparing the simulations and data. And of course, I would not be an observer if I couldn't end my talk by saying that we need more observations. So Cooper et al. Posted a paper on arXiv with showing you that, with publishing that paper 3 days ago. And that's the current count of known systems that will be detected by LISA. The red dots are the attached white dwarf binaries. Most of those are ours, or many of them. And it's both more than you might think. It's actually a couple dozen sources. But it's much less than it should be. Models predict there should be at least hundreds of LISA binaries that should have electromagnetic counterparts. The sky distribution tells you part of the answer. People just haven't looked in the southern hemisphere yet, and certainly not in the galactic plane. So there's more progress to be made, and I think where it gets interesting, if you can make this plot into hundreds of sources, you can really start doing populations and not just looking at individual systems. So there's interesting paths forward here. Thank you.
In addition to discrete sources, as we know from X-ray astronomy, there is always a background of fainter sources below the detection threshold. What would that look like?
It looks like this. So this is the predicted source distribution of objects in the LISA passband, where you're plotting gravitational wave frequency versus the characteristic strain. The cloud of blue dots is the individually resolved white dwarf binaries in the galaxy, but this gray band is like the other 100 million, literally, compact binaries in the galaxy that you see just blur together into background glow. Oh, it's a background. It actually it reduces your sensitivity here, right, at these frequencies. But it's a measurement. So the shape and amplitude of that is a direct measurement of the overall population of double white dwarfs, or double. Actually, they're almost all double white dwarfs. There are some neutron stars objects too, but this is a direct measure of the entire population of compact binaries in the Milky Way. So it's actually a measurement, but it is also noise.
And what's the expected background from supermassive black holes? Is that?
Well, they transit through, continuous sources. Well, LISA, these bands are that, right? So these are the tracks for emerging pair of supermassive black holes.
Right, individuals.
Yeah, and they move through.
Is it on lower, much more on the left frequencies? It's like with PTA, not the LISA.
Right, with PTA, but it extends also to higher frequencies.
Yeah, so they have, there's a whole talk on this
Is
slide.
it above the galactic or below?
Yeah, no, it's well above. I mean, so out to Z of 20, you can detect these things merging, and they track through. And the really cool ones are the ones down here. These are like sources that will pass through the LISA band and will become LIGO sources a couple months later. But these sources are changing, right? These are essentially constant frequency. These are moving through the plot, so they're you'll see them move through cross frequency space.
Questions? Go ahead.
So Warren, thank you. Is there a confusion issue here? Is there a risk of there being so many sources and you only have a limited amount of signal that you just get confused?
Yes. So it's very similar to what Avi was asking about. So there is confusion, and you only are expected to resolve individually about the loudest 10,000-ish compact binaries in the galaxy. And the reason why is that if it's too faint or too low sync to noise, it just blurs in with everything else. But the loudest, the the brightest, so to speak, 10,000 should be individually resolved.
Can you detect also a Jupiter around the white dwarf or not?
No, I don't think that'd be
Okay.
sufficient.
Go ahead.
Yeah, very cool. You mentioned that the predictions are still very uncertain because, post-common envelope separations are very uncertain, but with this combination of multi-messenger, how hopeful are you about constraining the post-common envelope separation distribution?
Well, as an observer, I think we've measured a little piece of parameter space, but we have an actual measurement. And so the tricky thing is how do you connect that to the simulations? Because the simulations are done on the parameters you actually can't observe, like mass, mass ratio, period we measure directly. But it's to do the population studies, you have to make assumptions. And so I don't know that there's actually a really great way of constraining that. I think what you can say is you can better resolve certain subpopulations that you know will be there. And so, for example, they break this apart. So you expect most of these 10,000 objects you resolve are double white dwarfs. Most of those are double helium core white dwarfs. Those aren't things, we found the first one just a couple years ago. Those are not commonly known now, but that's most of what LISA will see. A helium plus CO white dwarf, that's the next most common source class that LISA will detect. Again, not so many of those are known. People always think of double CO white dwarfs as being the common thing, but that's actually the least common class of object that LISA will detect. And maybe tens and optimistically 100 binaries in the Milky Way that have a neutron star in them. Because those systems just aren't at the right frequencies.
And so for observing them in the EM, do you have hope of also getting more of the helium white dwarfs?
Sure. Yeah, the helium white dwarfs are low mass, so because they're degenerate, they're larger in radius. They're actually easier to observe in some ways, but they're intrinsically rare. So that's why you have to do these design and experiment to find them.
And Warren, will it give us a new sets of constraints on GR, general relativity, just because we have both electromagnetic and gravitational?
I don't know about that. I mean, the pulsar timing's got to be anything to do with white dwarfs.
Is there any delay, I guess, between the two signals? But
Perhaps. Again, I think pulsar timing's got to beat you in terms of accuracy and precision. But I mean, what you're testing are things that you can't do with the neutron star of the black hole. You're testing mass tidal, theory. You're testing mass transfer physics. You're testing things you can't test with two pair of black holes, and you're testing it well because you have. I mean, the best systems will be both bright and light and in gravitational waves, and those are the systems you can really do good physics with.
any other questions? Go ahead.
Yeah, I have like a general question about LISA. I tried to ask it to several LISA people and never received a decisive answer. So LISA is not like a telescope. It cannot point. It basically detects, it sees everything. So doesn't it look like, you're trying to detect a supermassive black hole merger. It's like you're trying to look at a faint star and around you have flashing lights of police cars at all possible frequencies which are very bright, which are your systems. So how do you actually separate the signals? So
people have worked through that very carefully. So yeah, so LISA detects the entire sky continuously, but it detects it in frequency bands, and so you can use frequency to look for changes. The compact binaries are mostly constant frequency sources. The merging objects are not. And so over time, you build up some noise on a constant frequency source you can then subtract out. And because the LISA goes around the sun in orbit, you see the sky in different polarizations. You don't care about that from an astronomy standpoint, but for detection standpoint, there's a phase change that you see on compact binaries that allows you to disentangle, position, for example, more than if you're just sitting there looking at the whole sky the whole time. So there's different things you can do to keep that out.
Any other comments, questions? Not, let's take, go ahead.
So it's probably just an aside, but in Wisconsin, there's a lot of work on blue stragglers with white dwarf companions, and more are being found in clusters all the time. I'm wondering if they play an important role in understanding the progenitors that are forming some of these more exotic white dwarf pairs, or is that really sort of a separate siloed area of research at the moment?
Yeah, there's a pair of objects suborbital few stars that have orbit periods. You have to be less than an hour orbit period to be an Ulrich source at least they can detect. So that really rules out pretty much anything that involves a normal star. It has to be a compact object or a pair of compact objects.
For some reason the microphone is not working, but maybe it's because it's hidden behind your shirt. Anyway, let's thank Warren again.
You might need multiple batteries.
The batteries are.
Yeah, I think it's batteries.
Nothing like no results. That's a good idea.
So I should use this one.
So they're a little bit, like they were supposed to. Then they got a little bit delayed.
Hello?
I muted it.
They're starting to.
Good to go? All right. I'm not muted. Can everyone hear me?
No, we are still not hearing the microphone. I don't know why.
Bring the microphone up a little.
Bring it up a little bit. Can you hear me now? Okay, it is.
Oh, there it goes.
Okay. All right, wonderful. Well, anyways, glad to be up here from New York and be fed as usual with the lunch talk, which is great. Sometimes they don't feed you as a speaker, and that's really, it's no good. Anyways, I'm here to talk to you about how spiral arms are metal freeways, specifically from this paper that just got accepted, but there's the archive phone number anyways. So I'll be talking about some results out of the Fire 2 simulations. So these are a suite of cosmological zoom-ins where we're simulating sort of one, really at this point, there's one Milky Way at the center of it, or roughly Milky Way mass galaxy. We include a number of forms of feedback, supernova, winds, ionizing radiation, and we track the metallicity, which is important. The resolution of all these galaxies that I'll be talking about, it's finite mass, so the resolution is 7,100 solar masses, so we're at a couple of parsecs. So that's sort of setting the stage. And then I'm going to blur them all out. We're only going to be talking about 100 parsecs and on up anyways. So with that, I'll start continuing. So a fun fact about galaxies is, generally speaking, when you're in the Milky Way mass range, disky galaxies have pretty consistent metallicity gradients. They're 0.025 to minus or to 0.05 dex per kpc falling from the centers, which are most enriched, to the outskirts. So of the 6 galaxies I showed earlier, here's 5 of them. I'll tell you why I blocked out the 6th one in a second. But they all have gradients in the gas that are consistent with things we see with manga, etc. So these galaxies, by and large, are fitting sort of what we expect. And there was some great work by Matt Ballardini at UC Davis looking at how these gradients evolve with time as these disks form. But I'm really interested in why there's this scatter. Where does, at a fixed radius, we have 0.1, 0.15, 0.2 dex scatter. Why do we see this? Is this related to internal processes, things like star formation and self-enrichment? Is it accretion? Is it mergers? Why does this come about, and sort of can we explain it away simply? And if we go from averaging azimuthally to just let's look at the distribution face on in one of your favorite matplotlib color maps, you can see that the center is, and this is in the cold and dense gas, so if we're making like a CO map and then somehow we can take that and turn it into a metallicity map, and I'll get to why I did that for this one in a second. But you see the center is enriched and it falls outwards and it looks pretty smooth, and you can't really see anything because the human eye is pretty bad at picking out very slight hue changes. Now if we look in something that observers might actually take a stab at, looking at the ionized H2 regions, same thing pops out, although it's a lot spottier. The covering fraction of H2 regions is necessarily a lot smaller than the covering fraction of gas in these galaxies. But if we go and subtract out sort of non-parametrically what the gradient is, all of a sudden we see, again, it's only 0.1 dex, so this is down close to the noise of a lot of these kinds of measurements, but I assert we can and soon will see these kind of things. You can see structure pop out. That along spiral arms, or what you might call flocculent arms in these galaxies, there are, over several kpc consistent structures where things appear that they're a little metal rich or a little metal poor compared to their neighbors. And generally speaking, they seem to follow the spiral arms. And so when this pops out, this kind of was what gave me the alarm bells of, oh, maybe there's something neat in here to look at. And if we look at this whole sample of galaxies, again, the one on the bottom right I'm going to talk about in a second, we see that this structure kind of appears to exist in some form across all of them, that there are blue and red streaks across them. Now, again, this is quite qualitative at this point. This is just like a barber shop pole kind of pattern. And then M12R, this one on the right, it's kind of messed up. It's been hit a couple of times by about like 3 LMCs in the last It's a Milky Way mass galaxy that's been hit by like 3 LMCs in the last year and a half or so. And so its gas disk has just been more or less whacked pretty good. So it doesn't have a consistent pattern. And I'll assert that this scatter is in the spiral arms and not some difference between the arms and inner arm regions. So if I just take a PDF of what you look like compared to your neighbors, are you metal rich or metal poor, and then try to ask, are you inter-arm or arm, which I just did with a simple gas surface density cut in some sense, there's no offset between the low gas surface density regions and the high gas surface density regions. The inner arm and arm regions appear to lie on the same Gaussian-ish looking distributions. Maybe the inner arm regions are a little bit wider in terms of their distribution, but by and large there isn't any consistent offset. So this might immediately make you think, well, I might think that as a spiral arm passes, there's gas inflows and you're triggering star formation, and so you're getting supernova, you're getting enrichment, and so maybe it was enrichment, and I should have expected there's some difference between the arms and inner arms. But if we then go and just say, okay, how do these arms, these KPC patches look as a function of their local star formation rate or their nearby star formation rate, and how we might compare that with observations, we see that over in these galaxies, about 3 decks in star formation rate surface densities, there's no consistent dependence on the metallicity. So if you were metal poor compared to your neighbors, you'd be low. If you're metal rich compared to your neighbors at a given galactocentric radius, you'd be high. There's scatter around 0. Observationally, this is borne out roughly. So in the back, there's a red and a gray band by Catherine Krekel. And you have a little bit of wiggle room in terms of the slope that they might see based on the calibration of how they convert their H2 regions to local metallicity. So observationally, there's either some dependence they might see or no dependence, again, depending on the calibration, the kind of calibration they do. So at least at first blush, in our simulations, we're not seeing any dependence on local star formation rate. But if you then go and color these with the same color map, which is it's a little trick that I'm trying here, and you color it by instead the ratio of the radial to tangential velocity. So to give you an idea of whether or not these regions are moving, any patch of gas is moving relatively speaking inwards or outwards, this pattern then again appears. And you can pick out some fun things, like in the center top one, there's kind of a super bubble that you're seeing where there's a region that's clearly kind of exploding outwards radially. And so you see both some combination of actual accretion flows, local bubbles that are forming from supernova, and just generally the dynamics of the galaxies. And so if I say, or if I were then to try to convince you that in fact there's something to do with this radial motion, I'll say it's borne out slightly, albeit quite noisily. So here, again, on the x-axis, we have just the ratio of the radial to tangential velocity. So, positive values are you're flowing outwards relative, at your radius, and negative values you're flowing inwards. And then if you're up high, you're metal rich compared to your neighbors, and if down low, you're metal poor compared to your neighbors. And so more or less, as you can see across this, again, noisy sample, that gas that's moving outwards, maybe unsurprisingly, because you're grabbing some patch of metallicity gradient, looks metal rich compared to its neighbors, and gas that's moving inwards looks metal poor. And so there's maybe some kind of conveyor belt action going on where as these flocculent arms exist, they kind of are slowly moving inwards at, again, only a couple kilometers per second. This is very hard to measure kinematically. But the signature might persist if we take some statistical sample of KPC patches of our galaxy. So this is in the cold and dense gas, which again, quite hard to change CO measurements into metallicity. But if you look at the H2 regions, more or less pretty much the exact same relation appears. And so if you're going to go out and measure the metallicity of a bunch of H2 regions, you might be able to pull this out. And so I'd like to convince you all that we're seeing this here. And then you might say, well, some of the ITC people in the room might ask us, well, oh wait, sorry, that's in 2 slides, never mind. So here's the simple argument of what's going on is if you have some metallicity gradient that pre-exists in your galaxy, which is built up by sort of the inside-out growth of your galaxy, for instance, or that's a typical argument for how you get gradients in Milky Way-like galaxies, well, as you have any radial transport, things that are coming in from the outside, well, they're metal poor, as they're more pristine gas at the outskirts of galaxies as accretion occurs. You go in some distance before you effectively mix with your neighbors, and then you kind of go back up to your gradient. And similarly going out, if you are slowly moving out of your galaxy, you'll take metal-rich gas and mix in as you go. And at least sort of just fitting this to the fire data, things seem to move for about half a dynamical time before they effectively mix with their neighbors in any given radius. So as you move sort of eddy lengths or scale heights, you can go out basically a scale height or so before you mix effectively with your neighbors. But this still might appear as an observational thing. Now, the theorists might say, well, how much does it matter if you have turbulent metal diffusion or mixing models in your simulations? And here's a couple of those runs where there's no turbulent metal diffusion, where you don't have any effective mixing between gas elements. You have the standard fire, and then just for one of them, we multiplied it by 10 just to see, that's kind of fun. Is there any effect? And clearly, I mean, this is well known that you need turbulent metal diffusion models in your simulations, in particle-based simulations, if you want a realistic metal distribution in your galaxy at all. But I would argue that as soon as you have some realistic or some amount of mixing, it's the larger scale dynamics, it's these, the gas flows that matter more so than anything else. And so once you start dialing it up even more, well, the motion between, or the exchange between particles doesn't seem to matter, but the same relation appears to exist. So you need some turbulent metal diffusion, but it doesn't affect this result. And so with that, the summary, more or less, is in these galaxies we see fairly clear metallicity gradients, which then, as there are these shearing motions and tidal motions that are carrying gas in along flocculent arms, only a couple of kilometers a second in or out, are appearing then in metallicity as 0.1 dex scatter azimuthally. And so at least some good fraction of the azimuthal scatter in spiral galaxies that have metallicity gradients might well be explained by actual radial motions. And so we might be able to, this might be a sort of interesting window in looking at the accretion flows and the sort of kinematics of spiral arms themselves. So I'll end with the joke that I'm from Los Angeles, and so I'm used to calling them metal freeways. But since we're in Boston, I guess they're metal highways here. So anyways, with that, thank you very much.
The galaxies don't just have gas, they also have stars.
Yes.
And the dynamics of stars is different than the gas in the sense that it doesn't respond to pressure. So, I mean, stars do migrate.
Yes.
We'll talk about it as a result of those fluctuations. But if you were to compare the gas to the stars, could you then validate your picture?
I think with the young stars, if you're looking at, if you're trying to do some measurements off of at least anything under maybe 40, anything Cepheids and younger, I think you might be able to see this and it might pop out as a relation. After that, I think there is probably just enough mixing that I don't know if you would see this so clearly. And between the arms, or sort of as stars evolve and their velocity dispersions relative to the gas, the asymmetric drift, I think it is wiped out fairly quickly, but younger than maybe 40 million years, I think you could probably see it in the younger stellar populations.
Go ahead, Tony.
There's an excellent measure of metallicity in CO, which is the ratio of the isotopic variance, 13CO, divided by C18O. And those two species are within a factor of a few of each other. At high redshift, they're very much weaker than the 12CO line, but it's a really good measure of metallicity, and it's observable in essentially all galaxies, even at very high redshift.
I did not know about that isotopic differentiation in terms of as a metallicity dependent thing.
Yeah, 13CO to C18O.
18O. Okay, thank you. Yeah. Hopefully, maybe you can go measure that.
Go ahead, Sarah.
Yeah, so how do worms actually survive compared to the time it takes the gas to flow inwards or outwards.
So I don't know if the gas would make it all the way in. Say, you join up out here, do you expect that it'll flow all the way along a single spiral arm down towards the center? From just, again, hand wavy looking at the videos, the arms seem like they're pretty coherent over like an arc of maybe 10 kpc, and that might cohere for 100 to 200 million years, but then as just other tidal motions pass through each other. So I think that any gas element might really make it and I think this is tied to the mixing timescale where, it might make it a couple of scale heights, maybe up to a couple of kpc, before other dynamic motions sort of wipe out that semi-transient feature. Because again, most of these are, in these flocculent galaxies, most of these are tidal or shear induced, and so they're somewhat transient as opposed to like a grand design spiral that's really a companion galaxy that's driving it for a giga-year or two. So it's not like a very coherent, like you show up at the door to the star factory, you go 20 kpc in along a spiral arm, and then you go 20 kpc home. So it's not quite that. Otherwise, I think the gradients would just be much steeper and narrower.
Any other questions? Yeah.
Hey, could you compare with, so you showed the correlations with the star formation rate. Do you compare with the long-term star formation of about 10 million years, because maybe to create like Kelp-Larsen size features 10 million years?
So I looked at, so the ones I showed you were 10 million years, and then I also looked at 100 million years to see if there was a longer term evolution. There's a negligible, like statistically, I'll just go back to here, it goes up maybe a little bit at the high end. And I think that some of that is if you can actually sustain high star formation rates for 100 million years, then you are really enriching yourself compared to your neighbors. But it's rare that any given region can sustain more than kind of one starburst or one GMC event. If you're saying, oh, well, every 10 million years a large GMC is going off, that's pretty aberrant in terms of super bubbles and supernova and stuff disrupting the local ISM. So there is some dependence if you look at longer time scales, but again, it's like longer time scales and very sustained high star formation rates. Mm-hmm.
Let's thank Matt again.
Thank you. There you go. All right. Hold something.
Can everyone hear me okay? Great. Then let's, 1 second to share this. Okay. Yeah, thank you very much for having me. I've been here a couple of weeks ago talking about something very similar, but I want to actually focus on mostly focus on the unpublished aspect today of my work focused around the origin of multiphase galactic outflows. The reason why it's unpublished is because I have usually this problem. I'm very good at simulating. I'm not as quick writing them up. So I have over 600 terabyte of simulation data, and I'm the computing board lead at my institute. So I'm the most active simulator at my institution. So I'm kind of proud of that, but I should speed up that part a bit. So sorry, yeah, I should speed up that part a bit. So when we talk about multiphase galactic outflows, we need to consider the multiphase ISM first, okay? Because that's where star formation happens. That's where we ultimately, inject the feedback and ultimately drive the outflow subsequently after, mostly by supernovae. So I brought you my favorite picture of the ISM, the Orion molecular cloud complex. So you have the zodiac of Orion here. So this is Betelgeuse, this is Rigel, this is the belt, and you have these 2 super bubble lobes around them. And there's a lot of stuff going on. So you have 10,000 Kelvin H2 heated gas. So this is photoionized gas. You have very cold dust structures. So they sit around 10 Kelvin. So there's a lot of multiphase gas in the ISM. And you have massive stars such as Betelgeuse. And they drive, most of the feedback in the ISM and most of the outflows. So that's a spatially resolved observation of Betelgeuse. The problem, when you look at this, so what you can do is you can ask your favorite, large-scale cosmological simulations such as, TNG, and study the outflows in there. And that's what people did. And it's very useful simulations to have, but they have some limitations. So for instance, what they cannot do is drive outflow self-consistently from their ISM because they effectively don't have an ISM. So they have a pressure floor at 10,000 Kelvin, so there's effectively like no cooling down to like the actual ISM densities, and you model this in a subgrid fashion. So the problem, or like the problem for the large-scale cosmological simulation community, which I'm also a part of, so I can say that, is that what you have to do to get like good galaxies at redshift 0, you have to typically adopt very high mass loading factors, okay? This is not at all what observations, at least in the dwarf regime, find. So this is work by Christy McQuinn, the black dots. And it's also not what we find once we go to this regime of like a resolved ISM, where we have very good resolution and model physical processes in very high detail. So that's a discrepancy, and we have to work through this. So ideally, we want to understand why those simulations need such a high mass loading, and hope we can improve with the findings we have on the small scale ISM scale, and hope to model, have better subgrid models for the large scale cosmological simulations. So let me talk about like what I'm doing to help this. So this is my latest simulation, fresh off the press. So we had a paper about this before Christmas. It's a large Magellanic Cloud type isolated galaxy, and it's fairly good resolution. So it has 1 solar mass resolution and 0.5 parsec spatial resolution. Was very expensive, so this simulation was like roughly 4 million core hours to run on a supercomputer. And we model a lot of things accurately. So for instance, we sample the IMF. So we have single stars in here. So every dot over here is a single massive star. That's already quite cool. Then we follow their far UV heating. We follow their photoionizing radiation, and we explode them as type 2 supernovae, core collapse supernovae at the end of their lifetimes, and distribute energy in metals. And the key aspect of a simulation like that is that we actually resolve the supernova feedback. So we get a self-consistent set of Taylor phase. So that means all the outflow properties that we can observe in these kind of simulations are driven by resolved physics. So that's the real big difference between like the simulations I'm doing and like what most of the rest is doing. It's not entirely accurate. There's a lot of people doing similar stuff. So then we are mostly interested in the outflows. So how do we measure outflows? In simulations, it's kind of easy because we have the full 3D data, right? So what we do is like we take slabs here at 1, 3, 5, and 10 kiloparsec. We define an outflow rate, which is this, like not very complicated, and an energy outflow rate, which is this. And we can basically measure this at these heights and then try to compute loading factors. And when you do that, what you will find is that you will get like, depending on where you measure at lower altitude, values around unity for the mass loading and slightly lower values at the higher heights. So it's just like telling you that there's not. But they're generally low, okay? So this is what I already mentioned compared to like the dwarf observations we saw earlier. This is like in fairly good agreement. For the energy loading, the story is similar. We actually don't like, remove so much energy from the ISM into the CGM, which is an interesting problem to have, because if your mass loading in your cosmological simulation is high, your energy loading is tied to, it should be higher. So it's also not what we find in our resolved simulations. So again, that's a problem for another day. The main aspect of this work that we had on the archive before Christmas was, though, to look at the multiphase nature of these outflows. So you can like make a phase diagram like this, where you have the outflow velocity on the x-axis and essentially the temperature or the sound speed on the y-axis. And you can look at like a mass-weighted, version of this. Then you will see that most of your mass is actually transported by the warm wind. And you can look at an energy, weighted fashion of this, and you will see that there's like almost integrated. There's a little bit more energy in the hot phase than it's in the warm. Which is for us very nice, because this is what has been earlier predicted by simulations of small patches of the ISM, such as Tigris or Silk. which some of my collaborators carried out. So we're very happy that this picture still holds in a resolved ISM global galaxy fashion, okay? So now what about the metals? So let's talk about the metals. Matt gave a great introduction for this. We looked at the metals in this simulation, and we get like, the story is the same. So this is the metal loading. We see there's, at low altitude, we get a high metal loading, and higher altitude, it's lower. Okay, fine. So now what you can do is you can actually look at something called the metal enrichment factor. It's a bit of a complicated quantity, but essentially it's the metal outflow rate over some, ISM scaled outflow rate, in the sense of like, it just tells you how over-enriched your outflow is compared to your average ISM metallicity. So if you keep your ISM at fixed metallicity and compute the metal outflow rate based on that, and basically divide the actual metal outflow rate by fixed ISM metallicity outflow rate, you get this plot. And what you see is it's fairly low at low altitude and high at high altitude. The reason for this is that most of the metals are actually transported by the hot wind, and I can show you this in the next figure. So when you look at the same phase space, you will see that most of the metals are carried by the hot. And the reason why it's higher, the metal enrichment factor is higher at higher altitude, is because this part of the wind continuously drops out as we move to higher altitude. Okay, so only the highly over-enriched hot remains. So why is this not, you could ask now, why is this plot not in the paper that we submitted before Christmas? It's a long story, but essentially there's a few things that, if we would run the simulation from scratch, you would have done a tiny detail different, which is like including a metal diffusion model that Matt already talked about. So this was one without a metal diffusion model, okay? The problem is this gives you this like very strongly over-enriched hot phase, which has no gradient down to the cold phase or the warm phase. And that you also see there's a lot of gas that sits at high metallicity down here, which is never mixed in. So our previous argument before we actually looked at this was we don't need a metal diffusion model because we're high enough resolution to get dynamical metal mixing. So we were a little bit, well, I was wrong, essentially, about that fact. So what we did then now, and this is a slightly smaller simulation for testing, we included a metal diffusion model. And, well, we get a gradient, so that's nice. But we also mix in all this gas down here, and essentially get like slightly over-enriched, warm phase here. That's very, very good, but it also tells us that we have to go back to the drawing board once in a while, and actually at the resolution we still need a metal diffusion model, which is like the big takeaway, and Matt basically already told us that, so we need some kind of metal diffusion model, even at this 4 solar mass, 1 solar mass resolution that we run out of simulations. So with that, I leave you with my conclusions, and I'm very happy to take questions.
One thing that you didn't mention is the importance of dust, because it has a high opacity, and
that's right.
Potentially radiation can drive the outflow in regions where dust is abundant.
Yeah.
And much more so than opacity due to heavy elements or electron scattering.
It's true, yeah. So there's like a short answer for this. We mostly stay in the low metallicity regime. So also our dust to gas ratio is fairly low. So that's the quick answer to it. But obviously, right, once we go into like a environment where dust is more important, we have to certainly think about that. And Chayu-Hu, one of my collaborators, actually implemented a dust model. So we're actually at the moment trying to rerun this simulation with the full dust model to see the effect.
And another thing you have to worry about is the black hole at the center of the galaxy, because at least the Fermi bubbles are driven by that.
You're right. So again, I'm very good at a simulating part, right? I told you, right? So there is a simulation with the black hole feedback as well, which we have not, done a lot with yet, because we are. There's a very long answer to why not, which I'm happy to tell you offline.
It's okay, you don't need to.
Yeah.
Go ahead.
Hey, great to see you again.
Yeah, nice
so
to
two
meet you.
quick questions. One, when you showed us the metal enrichment, is that a linear or a log plot?
Oh, sorry. Yeah, that's not a log plot. That's a linear scale.
It's a linear
Yeah, so that's actually a factor for maximum over enriched. Yeah, but to be entirely honest, there are very high metallicity particles in a non-diffusion simulation. So the highest metallicity what I get is like 20 solar masses. But it's like an outlier particle, so I'm not necessarily worried about that. The bulk but the bulk is still too high. That's why we thought about reiterating this with the metal diffusion model. And we were a little bit, sometimes you get carried away when you have very high resolution and fall for specific things that might actually not happen as you thought they should happen, right? And that's why, like, one of these aspects that we need to improve, but we're working on it, right? So, yeah.
The second question was, do you track inflow as well as the material back end?
We do. We haven't we did not make a big fuss about this in that particular work, but essentially, if you, well, actually, it doesn't really matter which one you look at. There's this stuff will escape. Most of this stuff will fall back. Okay, and that's so essentially this stuff here is your fountain, and this stuff really escapes. So because this is mass biased, right? There's a very high inflow rate, so there's a lot of recycling of the gas happening for sure. Yeah.
Go ahead.
I'm interested in how physically realistic the mass loss rates and wind velocities of the evolved stars in your simulations can be. I remember with stellar models, you get sort of an average, overall the mass loss rate is correct, but instantaneously.
You mean from stellar winds?
Yeah,
No?
from stellar
So,
winds. How are you dealing with AGB episodic
yeah,
mass loss?
well,
and things like this?
so this is the part of the model I'm not super happy with, because this is all the idea of a simulation like this was always to be as resolved as possible. So we can do this for the supernova feedback because we can actually resolve the set of Taylor phase at the resolution we are. And I wrote a very long paper about that. You can actually do that. The problem with the AGB stars and stellar winds in general is they are very hard to handle numerically. So whatever you put in is a subgrid model. And even if you have 10 times higher resolution than I can currently run at, it's a problem. So we have AGB stars in there actually. So what we do for them is they basically live on a few time steps of the actual simulation. So I just do one metal dump at the end of the AGB star phase. And there is some, actually you can see the AGB star enrichment very nicely here. So there's some 1.5, this gas here is actually AGB star enriched. But to what degree that's correct, we haven't checked, right? It's a very good point. The stellar wind models in there, there are some present, but I would not bet my life on them, so to speak.
Well, I guess there was an advantage in the old days to say, let's shove all the uncertainties under the rug because the resolution was not good enough. But
yeah.
Now you're getting for the first time to.
No, it's the beauty of subgrid models is that you don't have to care about a lot of these things, right? So that's why it's great that we suddenly can care about why is this how can we improve such a resolved picture, right? So that's I think great progress in that particular subfield.
Let's thank Ulrich. We have to move on. Sorry about this.
Can you hear me okay?
Yeah.
All right, going back to Orion, we did not plan that, but I'm going to be talking about the search for transiting exosatellites, moons, and planets in the Orion Nebula cluster, although our group is very interested in extending this work and considering other nearby star-forming regions. So first off, I'll just break into why should we be searching for moons at all.
I feel like the sentiment is sometimes that moons are sort of accessories or appendages of planets, kind of an afterthought, not that interesting to the exoplanetary community or the stellar formation community. But I will argue that we're seeing moons forming alongside planets, that they can impact the formation and evolution of planets. That's most certainly true if you think about moons like our own system's moon, our own Earth's moon, where they're formed by giant impacts most definitely. And so to better understand exoplanet formation and evolution broadly, I think we do need to understand moons. Moreover, they are also worlds. So when you hear this worlds and suns in context, NASA decadal survey primer of a key component we should be thinking about, moons too are these worlds. And in fact, there are many signs that they could offer the key ingredients for life in our own solar system. Liquid water, energy sources, protective atmospheres, organic compounds. When I'm talking about our search for moons with this particular survey, TEMPO, I'm thinking of really something akin to the Io-Jupiter-like ratio of radii, really ignoring the fact that there will be moons formed from giant impact events like our own Earth-Moon system, but really we're talking about a difference of an order of magnitude in terms of those radii. But we're really thinking about these kinds, which are much more commonplace in our own solar system. In fact, they outnumber planets in our solar system 200 to 1. But we have yet to have a confirmed exomoon outside of the solar system yet. Okay. However, free-floating planets, I don't know how many people have been hearing about this. And when I talk about it, I realize not a lot of people have heard about free-floating planets. They have been found in great abundance in several different systems. And I want to point out that when they're young, shown here by this blue curve, this is a 10 Jupiter mass, 3 million-year-old free-floating planet. They're actually bright in the infrared, and so you could easily observe them with an instrument like Roman. Here we're seeing two different Roman filters, the F146 and the F213. And in fact, you could monitor them for transits much the way that Kepler and TESS monitors host stars for planets as well. Or you can monitor them for exomoons. So this transit technique, I think, can play a prominent role in the detection of young exomoons and exosatellites. But you'll need to avoid contending with a host star. Fortunately, we are finding many free-floating planets in systems like Upper Scorpius. There was an analysis of that system, which is 10 million years old, a range of 70 to 170 rogue planets. This range really has to do with the fact that it's difficult to classify whether or not you're dealing with a brown dwarf or a planet because they do change so abruptly in spectral type as they're cooling. And there is a range of ages in many of these systems. But in fact, we see them also in the Orion Nebula Cluster. They have been counted by Hubble's Space Telescope legacy data. They have yet to be monitored in the time domain, however. However, we will soon be seeing an exciting satellite joining the contingency, and that's the Nancy Grace Roman Space Telescope. The wide-field instrument in particular is quite interesting. It is very similar in terms of its spatial resolution to the Hubble Space Telescope, but it boasts 200 times the field of view. So you're dealing with a much larger field of view that you can contend with. And in fact, the bandpass extends beyond the optical to this 2.13 micron range. In addition, it is really one of the first big data surveys in space. It will be downloading 1.4 terabytes of data each day. So the ability to use something like this to do something in the time domain, in the infrared time domain, I think is a really exciting opportunity. So we've been proposing to do this. This is not a proposal that has been accepted. And we do have some simulations and works that we've published talking about what the yields would be that accompany this. The first region that we propose to do this for is the Orion Nebula Cluster. This is showing you the field of view of what the Roman footprint would look like. In green there, you see the Hubble Space Telescope field of view, and you get a sense of what the full moon would look like. So we're really talking about a wide range. And in addition to monitoring the free-floating planets that we know to exist in these regions for transiting exosatellites, there's lots of more science that one could do, and I'm very interested in talking with anyone about what you would do with a 30-day time domain observation in the infrared of a young star-forming region. We expect, just based upon that Hubble Space Telescope legacy data, to be monitoring 5,000 field stars, 2,000 young Orion Nebula Cluster stars. These are between 1 and 3 million years old, 560 brown dwarfs, and about 400 free-floating planets that have been observed. And our expected detections are shown as follows. There's really quite a wide range you'll see in what we're expecting to find, and that's because there's so many unknowns about whether or not some of these hosts have extended hydrogen and helium envelopes. Were they formed in situ free floating, and so they've maintained these envelopes all their lives? Are they ejected violently, and therefore their gaseous envelopes look quite different? These are all things that we contend with in our paper. There's a paper that's by Limbach et al. That I'll show you the phone number for shortly, that really talks about sort of the more conservative and more optimistic yields that would accompany these underlying assumptions. Regardless of whether you have a conservative or a really exciting yield in terms of the number of objects, it's still a really important parameter space for discovery that has an opportunity to answer lots of open questions and probe the low mass end of the IMF down to this very low mass regime. Our paper, this one led by Limbach, who's a graduate student that's about to wrap up at Texas A&M, looked at what the minimum detectable satellite radius that we could observe with a 7 sigma statistical significance. And we see that we're able to probe down to the radius of Titan. This is in, depending on which regime you are in terms of the host mass in Jupiter masses. And there's really a lot of unknowns about whether or not you're dealing with a rocky object or you're dealing with something that actually has this upper limit that's set by a very extended hydrogen and helium envelope. And I'll also point out, like I talked about earlier in my colloquium talk, that we're really extending beyond this sort of more well-known discovery space of sun-like hosts down to now this brown dwarf gas giant regime, which I think is an exciting place to be. So we have run some simulations to try to get a sense of what would accompany a 30-day observation monitoring these sorts of hosts. And we're looking here at just hosts that are in the gas giant regime, in the brown dwarf regime, in the stellar regime, and looking at various host companion separations. And I want to just point out where the Earth's separation would exist on this plot and where the Galilean satellites would exist, both in terms of host mass and separation, to give you a sense of really this large parameter space that we're exploring here. And our simulations are as follows. Give you a moment to just kind of look this over. But the different sizes of the circles represent the different masses of objects that we would be sensitive to revealing. In fact, we would be looking at a regime that is really sort of this proto-habitable, TRAPPIST-like systems. And I think this is a really exciting thing that we should consider doing as a community, and I'm very, very keen to collaborate both in terms of the science that I'm talking about explicitly here, but also beyond that, and think about what other science might we do in terms of maybe doing some direct detections of planets that are down to sub-Neptune masses, thinking about young stellar objects and their variability and investigating that. Looking for more Dipper stars like I talked about earlier that might be accreting and also might be showing disk occultation signatures from the disks that surround them. Creating near-infrared extinction maps of the dust in these regions, and then possibly offering more constraints on the low mass end of the IMF. And we're putting in a pretty lengthy proposal now we're calling Tempo++, where we're trying to create a product that would allow people to do these sorts of yield calculation simulations on more regions beyond just Orion, offering this as an open source code in Python, and exploring what sort of challenges and strengths would accompany various regions like Rho Ophiuchi, Westerland 2, and I'm very excited for the possibility of collaborating and talking about that with other people who might be interested. So big takeaways is that the Nancy Grace Roman Space Telescope is launching soon. Early 2027 is at the moment the date I'm hearing. I think that it's sort of being held under the radar a little bit because there's so much excitement with JWST, rightly so, but I just want to argue that this is really quite exciting, some of the capabilities that it's going to offer, particularly opening up into the infrared and expanding the field of view that Hubble was able to give us, has been able to give us. And indeed, we can leverage that instrument to perform time domain surveys in the infrared. We're hoping to leverage Roman in very much this regard. You can do this in one pointing if you like. You could even return many times to the same location. That's really wonderful because then you can get astrometry of these low mass objects. And that astrometry could tell you whether or not kinematically they're distinct from the local stellar population, which could then say maybe they were ejected, maybe they're formed in situ. So lots of open questions there. Yes, and there's lots of other constraints it can offer to the scientific community, and I'm super keen to hear about others that you might have in mind. And with that, thanks.
The free-floating planets, obviously they're not warmed up by any nearby star, so did you evolve them based on the internal heat? That depends
Exactly
on
the case.
obviously the detectability depends on their age, right? So you took that into consideration.
Exactly, yeah.
It's just thinking about for their leftover energy from their formation, and then thinking about how that cools as a function of time and changes their spectral properties.
So
Yeah.
they're mostly young.
So in the Orion Nebula cluster, the ones that we're proposing to monitor are between 1 and 3 million years. And there are other systems where you can still see them at 2 microns, where you're in the 10 million year regime. But you're constrained to have young in terms of 10 million years or so systems. Yeah.
So what information do you exactly expect from the time domain aspect of it? And will you have any advantage if you had, let's say, a 10-year baseline?
What do you mean by what information? Like what data products am I going to be looking at?
I mean, like, how will it help telling that this is a free-floating planet, or you are trying to talk about the continuous monitoring to get them from transits?
Yeah, to get the light curve, to measure for transits, to try to distinguish what's the host variability like of these young substellar hosts. So there's some, if you're just interested in the host in general, there's lots of science you can do there as well. But then also to get photometric information in terms of the locations of these objects and therefore kinematics when you return back. And to get a sense of whether or not there's sort of distinctly different proper motions than you would see from the Gaia data, which these sources, just for reference, are fainter than the Gaia limits. So we could compare them to the faintest stars that Gaia has been able to monitor to try to see if there is something dissimilar about their kinematic properties that would point towards ejection.
Because we have a deep image of Orion in the K-band, like K21 perhaps. It's probably the best ground-based image of the Orion Nebula. We took it for like PR purposes. It's here, you can find it actually in the walls in the CFA in some places. And this was taken in 2012, so this might be a good reference point, good baseline for proper motion measurements.
Oh, thank you. Yeah, that's great. Down to what magnitude, you said?
I think it's 21, so it's pretty deep. It's 25 minutes of integration with 0.2 arcseconds seen.
Okay.
So
I know when we co-add frames and we think about this region, we're able to probe down to about 29th magnitude. So when we're talking about the direct imaging, that's really what you can get the full duration. But for the monitoring, it's not too far from that magnitude range. So that's probably very helpful. Yeah, thanks.
Okay, if there are no more comments, let's thank Melinda.
Do you know about the deep image? That's pretty cool.